Yeah, I'll record it and then we can send it out.
Awesome.
Cool. All right, yeah, so this week we're going over signal processing. That's basically a technique where you can pass in some kind of signal, some kind of data into a function. This is just like a generalized way to look at it. And then out of that function, you get your process data. So this is just like a way we like to look at data processing and machine learning in a lot of the time, because it just helps us formalize various different frameworks. So you can think about most data analysis problems like this, and your data here can be any signal, whether it's EMG, EEG, FNIRS, all of these different kind of signal types, like depending on how you record the data. Your data can be in any of those forms. And then your function can be like a process that's going to have many steps, right? First, as we talked a little about last week, you have your data cleaning steps, which basically just throw out the noise in your data. And then you might want to perform feature extraction, which basically pulls out the relevant bits of your data. And then you have your actual data analysis, where you analyze those features and determine what means what. Like if you have a bunch of spikes at the start, then what does that mean, and so on. So the result over here is something related to the problem's goal. So like maybe you want to determine whether someone wants to click a button based on their EEG signals, or move a cursor, or write a word. And Jesselyn's going to talk more later on about how we can actually, like in a real world setting for our project, how that worked, this kind of result based thing. So yeah, the first step in signal processing is going to be data cleaning. We talked a bit about this last week, but the main thing here is that you just want to get rid of the noise, because when you're recording EEG signals, you have all these kind of fluctuations from like additional muscles, like from your brain, just from the environment. There's going to be all kinds of noise. So to get rid of that, the first thing we do is throwing out the bad channels. So we have like 8 different electrodes that like sit across the person's skin. Maybe one of these electrodes is faulty or it's in the wrong position. We can actually just throw out like a channel like that. And if we stick to throwing out that channel for all of our data collection, then we should be fine. And then after that, we want to clip the recordings to the same time frame. So that basically means if we're working with a data analysis method that requires us to that only allows us to deal with like 2 seconds of data, because that's how some data analysis methods might be later on, we'll see, we're going to do that clipping. And then after that, we have a simple bandpass or some kind of pass filter. And that basically just means that we only include frequencies in a certain range. So again, as I mentioned earlier, there's a ton of noise, so that helps get rid of that. So you can see over here, this like one frequency, like F0, and then we have a couple other frequencies, like some amount to the like lower frequency, some amount higher frequency. And then we basically just scale the amplitude. I think this is like dB, right? Decibels. But in our case, this would be, or I'm sure you can actually measure all kinds of amplitude in decibels. But yeah, you basically just scale across the various frequencies by their, you scale the amplitude across the different frequencies. So you want to only have, you want to maximize the relevance of this frequency, and you want to throw out noise that's like too low or too high. Yeah, does this data cleaning stuff make sense so far? Cool. Okay, so then there's feature extraction. We actually don't always have feature extraction. This was more common with classical machine learning models, where we would have to do some kind of feature engineering before feeding it into our model. But nowadays with neural networks, we don't really have to do much of this feature extraction. But it's still important to know about it, because they can actually come in handy sometimes, even when you're just like doing data cleaning or something like that. So one way to extract features is a Fourier transform. And this basically decomposes your wave into many simple sine waves. So for example, over here, you have a pretty complicated kind of wave. Wait, actually, no, I think this is a wavelet transform. Yeah, that's a wavelet transform. Yeah, this is the Fourier transform, but Oh yeah, if you look at down at the bottom one first, so let's say this is some like fancy EEG wave, we can use a Fourier transform to decompose that into these three other waves. And if you just stack these waves up on top of each other, you get something similar to this EEG wave. I was going to say something else about this. Oh yeah, but oh yeah, so, some of the time this might not be that good, right? Because EEG waves, they aren't like completely regular. They can shift all the time. So that's where wavelet transforms come in. A wavelet transform is basically similar. It's similar to a Fourier transform, but it allows you to change things over time. So this is like a bad example in the sense that this again is repeating data, but a wavelet transform lets you use these tiny little wavelets. There's like a few different types of wavelets. Like there's this one. They have names. I think this like I'm pretty sure it is called the sombrero, like something like that. And you can stack these different wavelets at different, like you can adjust the frequencies of all the wavelets and stack them in different ways, and that basically allows you to in a more dynamic way, I guess, predict how to decompose these more complex waves. um, Oh yeah, also when you have when you decompose the Fourier, like the wave here with the Fourier transform, your features then become like the frequencies of each of these waves. So um it's not like you're going to be feeding in these waves necessarily. It's more just like we have one wave at like frequency X, one wave at frequency Y, one wave at frequency Z. Um, and then we can feed that uh into our machine learning model. Oh yeah, this is another way. These are some other ways to do feature extraction. Principal component analysis basically identifies the principal ways, like the principal components that vary in your signal. So I think, yeah, that's this left one, I guess. Yeah, this is probably kind of hard to understand. But the way you can think about principal component analysis is that you ask the PCA function to find like some number n of principal components, and then it looks through your data and it finds the like biggest eigenvectors, which basically means like along what axes um, does the data vary the most. So like let's say it's similar to Fourier transforms in the sense that like these are temporal axes, right? Like we could say over over the over the yth frequency, that's where we see the most variation. So it's going to pull that out as like a big principal component. Or across the zth frequency, that's like the next most variation. So we'll pull out that one. Um, and actually, I think that's a bad way to say it. This one would be the principal component over here because this is the highest amplitude um, decomposition. So this would become our principal component, and then this would like first principal component, and then this one would probably be the second principal component. Whichever one has the second highest amplitude. So principal component analysis is just like another kind of mathematical way we can go about doing something like a Fourier transform. Um, though again, it is sort of it's more dirty in a sense. Like Fourier transforms have these like very elegant kind of waves. Principal components can create like all kinds of weird um, they can pull out all kinds of weird principal components. So like this second one over here, um, I think, is this a different example? Or oh yeah, over here. I mean this one. So on the top we have the principal eigenvector, the first one, and then this is the second one. You can see how the first one is like pretty much a sine wave. This one's also pretty much a sine wave, but there's a lot of noise in the data. Um, so the PCA can handle that a lot better, from what I hear, than a Fourier transform. Um, and then an independent component analysis is also like, again, these are, in a sense, these are all like just uh, different mathematical ways to get a similar thing. Um, I believe technically your principal component analysis is going to only like pull from the data itself. So like it will like all of like everything that comes out of a principal component analysis is going to be somewhere in your data, whereas your independent component analysis almost reconstructs it in a certain way, even if there is some kind of noise in your data. So like your Fourier transform, that's probably going to be more similar to your ICA than your PCA. So yeah, over here are some like mixed signals, and then your independent component analysis basically like reconstructs a clean signal version of that. And I believe this is the main kind of feature extraction step that we're doing in our subvocal recognition project. It proves to be pretty useful, I think. We don't have to go over this. Just note that there's like more complicated feature extraction algorithms. Common spatial pattern is basically an algorithm that lets you localize waves depending on where they come from. So like you can perform common spatial patterns and find, it's almost like a PCA over space. So if you have like EEG signals from all these places on a person's head, you can use common spatial patterns to decide where each of the signals come from. And the graphs, like I was working with generating these graphs over the summer, and my research advisor was sort of talking about how these are kind of misleading. The red is actually the place where you find the lowest lowest amount of that wave or something. So common spatial pattern 1 would actually be like something emanating from the front of the person's head, like the prefrontal cortex. Don't take my word for that though. I just remember he was talking about like common spatial patterns are kind of anti-logical, like the way they're depicted is kind of backwards. Riemannian geometry, I honestly have no idea what this is. Someone like a professor I was talking to a few months ago said that it's like a rapidly developing kind of technique, but I don't think I have the math intuition necessary to like understand it or even explain it. So that's just on the slide if you want to look into that more on your own. So yeah, once we've generated those features, or actually any questions at this point about these past few slides? Some of these are really like kind of elegant ideas, like the Fourier transform. 3 Blue 1 Brown has a really interesting video on this that you can look into. Yeah, any questions on this stuff? Oh, there's a question in chat. Oh, okay, nice, cool. So yeah, now we can look into machine learning. So the basic idea behind machine learning is that, or at least supervised machine learning, which is what we're talking about here. The basic idea is that you're given a bunch of data and you want to learn how to how to decide certain things about new data. So, or let me phrase that better. Like let's look at this graph over here, right? Let's say we have like height on the x-axis and like radius on the y-axis, and then these are like apples and oranges or something like that. In a supervised machine learning problem, which we're talking about here, we are told that all of this data is apples and all of these data is oranges. In other words, these data are labeled. So we know that the data point that is at like a weight or a height of 3 centimeters and a radius of 2 centimeters, we know that this data point is going to be an apple. And based on all this data, then we basically are fed new data and asked to make a judgment based off of it. So now we're fed this new data point, which has like a radius of 3 and a height of 4, let's say. And then we're asked to say, is this an orange or is this an apple? So that's a classification task. There's also regression tasks, which we'll look at, but just based on that, we can look at this first machine learning algorithm. This is k nearest neighbors. It's a super simple algorithm. It basically just looks at um, all the surrounding points of, so we're given a new point and then we look at all the surrounding points and the k nearest neighbors, or the k, so we pick k, like k is any constant that we pick. We can say like k is 5, and then if k is 5, then we're going to decide what this new example is based on the 5 nearest neighbors. So the first nearest neighbor might be this one, then 2, then 3, then 4, then 5. And out of those 5, like 2 of them are going to be oranges and 3 are going to be apples. And because of that, we'll say this new example should therefore be a apple, because there's like all, like the 3 out of the 5 closest neighbors are apples. So that's why we classify it like that. Whereas if we pick a k of 1, then the nearest neighbor, the one nearest neighbor, is an orange. So we would classify it as an orange in that case. So that's k nearest neighbors. There's also naive Bayes. This is a more probabilistic approach. I'm not going to go into the math. You can go over to SEAI for more of that stuff next quarter. But basically, the idea is that we find the we find the probability distributions of each feature in the data set. So for example, with this data set, right, we know that the height, for example, is going to peak in frequency for like much higher than for the apples than for the oranges. Like the average height for the apple is going to be higher than the average height for the orange. And similarly, the average radius for the orange is going to be higher than the average radius for the apple. And we basically generate probability distributions for each of these that depend on the standard deviation of each of these data of each of these classes. And then we combine that information in a certain way to basically predict the likelihood of any value being any data point being any specific class. So like over here, we might actually have a boundary, like somewhere over here, that's going to be 50%. It's going to be like a probability boundary that says 50% orange, 50% apple, because in this general area, the probability distributions just overlap very closely, and we can't say very effectively which one it's going to be. So naive Bayes is especially useful in those kinds of uncertain contexts where even we might not be certain about what we want to do with the data, and you can even just use it for data visualization. It doesn't even have to be a machine learning task. It kind of lets you visualize all the probabilistic, like all the data distributions in a sense. So it's nice in that way. And then, so any questions about those real quick? Don't get spooked by the math. This basically says the likelihood that X is C. Okay, you know what? I won't go into this. But yeah, the main idea here is that we're just finding those probability distributions. But yeah, any questions on that before we look at these next few algorithms? Yeah, so it's just about the size, right? So it's not even about distance. This kind of radius graphic is misleading in that way. It's literally just about the nearest neighbors. So like the k number of nearest neighbors. So if we have like one over here, that's like 0.01 centimeters from the point, and then another one is 0.02 centimeters, or like 0.011, something like that, we're still only going to pick the one nearest neighbor. It's completely about the number, not about the distance. Yeah. Cool. So let's look at some other machine learning algorithms. Support vector machine is over here. This is a classification algorithm again. It basically just finds the line, or technically the vector, that best separates the data, i.e. it finds the vector that has the largest margins between the surrounding data points. And this is also useful because you can look into what the margin ends up being, and that helps you make understand the data better. Sometimes SVM might not be able to even perform that well because your data is going to overlap a bit. It still performs in that sense. It has like backup methods for doing that, but it's not going to be as good. Also, SVMs by default are linear. There's something called a kernel trick, which you can look into more if you want to get more into like classical machine learning, that allows you to do a nonlinear SVM. But by default, you can only separate data with a flat line. And everything we're doing so far can be generalized to higher dimensions. So like over here, we're only talking about height and radius, but you could add another dimension for like weight or something like that. And you can generalize this to higher dimensions. Same thing with SVM, that goes for everything. You can, this is like the fact that we have 2 dimensions here is purely just like a visual constraint. Our actual data can be any like dimensionality that we want. And that dimensionality is basically just the length of the vector, right? Like with your Cartesian coordinates, or your like 2-dimensional Cartesian coordinates, you denote each point by like an ordered pair or whatever it's called. And that's basically just like a 2 vector. But if we have a very high dimensionality, we could even have like 100 or 300 dimensional vector, and we can still perform these kind of classification operations on those. So so then let's look at a logistic regression. Logistic regression is another classification model. It's this orange line over here. It basically is just it's technically called a regression, but it's not a regression. It regresses, but it performs classification. It doesn't mean regression in the traditional sense. But basically it just forces the data into these 2 binary classes. If you have data over here, it's going to be like pushed in this direction. If you have data over here, it gets pushed in this direction. And yeah, it's a pretty simple idea. Linear regression is probably something you've worked with before in like a stats class. It basically just finds the line of best fit for our data. So if we have like a bunch of data points all around here, and like they're broadly sloping up and to the right, then we're going to find a linear model that goes like that. And the power of a linear model is that we can now feed in any data point, and we can then get like a regression score for it. So like 0 to 1 over here could be like the radius, right? It could still be the radius, but let's say we're only given the height. So we basically want to learn a linear model of the radius when we're given the height. So if we learn this linear regression model, we can basically then just feed in any new height, and then we can learn to predict, and then we're able to predict like what the radius on average for that data point would be. So yeah, that's what a linear model is supposed to do. So that's the main difference between like regression and classification. Regression gives you these continuous scores, and classification splits something into discrete parts. Yeah, any questions about that before we get into deep learning? Okay, so I can't really teach you all of deep learning with a single or like a couple slides. This is a super quick overview. But basically deep learning, like if you look at this one over here, this is probably the most encompassing kind of what's it called? Kind of graphic or diagram. You feed in these like data points, like n data points, n dimensional, right? And each of these data points get paired with a weight vector. This weight vector is basically a list of parameters that we learn over time. But right now what we basically do is we take the dot product between this input vector and this weight vector, which is the same thing as multiplying each of the weights with each of the inputs and then summing them all together. So yeah, we do that dot product. Then we add in a bias term. I'm not sure why it doesn't show that here, but we add in another term that we also learn. So all these weights and that bias that we add in are going to be parameters. And then we pass that through an activation function, which introduces a nonlinearity so that we can actually learn a nonlinear decision boundary. And then we output some prediction. And this is basically a neuron or a perceptron. This is like the fundamental piece of a neural net. It takes in this input, uh, combines the input with these input parameters. Sorry, with these like learned parameters, and then we put it through a nonlinear function, and then we output it. So every single neuron in our big neural net is going to actually be performing this operation. Uh, and then when we stack all of these neurons together, basically it allows us to learn really complicated functions. Because if you think about it, this function up here, or this final output, this is a nested function that takes each of these as inputs, and each of those takes each of these as inputs. So you get this really complicated, huge function that has a ton of different like weights, like all these parameters that almost like little dials that you can adjust, right? You have all these little dials that you can adjust to change how this output, um, how this output, how this results, how this result gets output. Um, and since we have all those little dials, we use a algorithm called backpropagation and gradient descent to actually learn what the optimal dials should be. Uh, Backpropagation is basically just this idea that since we have nested functions, um, we need to use the chain rule to learn the uh, to learn how to change each of those parameters. Um, because each of these functions are like nested, right? And we can't actually take the derivative of those parameters without like tracing back through the function. So backpropagation is basically just that idea that we need to backpropagate through our neural net to learn what each of these parameters should be. So once we've decided how to move those parameters, right, each of these weights and biases, and we want to move them in such a way that our accuracy increases or our loss decreases, which is in some way, some of the time, the inverse of the accuracy. But yeah, we're just learning how to change these weights to learn a more optimal decision. And once we've used backpropagation to decide how we should change it, or the gradients for each of those weights, um, then we use gradient descent, which basically actually goes through and optimizes each of those weights. It's super simple. It basically just adjusts. Do I have that here? No. Yeah, it basically just adjusts each weight in the direction it's supposed to go. So let's say the third weight in this first neuron of the second hidden layer, let's say that that weight should be increased if we want our model output to be correct. If we want to increase it, so we determine that it should be increased based on backpropagation, and then gradient descent goes through afterwards, and it says, okay, let's increase this by like 1.5 or something like that. And then gradient descent basically just does that for all of these parameters. And it's called gradient descent because you're descending down the gradient of the parameters with respect to the loss, or the gradient of the loss with respect to the parameters. Because we want to decrease the loss or the inverse of the accuracy by adjusting our parameters. And on the left over here is a convolutional neural net. Or any questions about neural nets first? What they're supposed to do, anything like that? Like, are you guys like, is this like a lack of questions because like I've explained it well, or Or like, do I need to repeat everything because like there's no understanding?
For me, it's more, you've explained it in a way that I can understand the information, but I don't know what to ask. Like I don't know what I don't know.
Okay, yeah, that's cool. I think yeah, I think a lot of this just comes with like looking at the information over and over again, and letting it like sink into your brain. That's one way to do it. Another way to do it is obviously just like build projects and like engage more with the material. So if you go to Santa Cruz Artificial Intelligence, that club is going to be doing a lot of this stuff. So if you want to look more into that, feel free to head over there. But also convolutional neural nets. So convolutional neural nets are basically just a type of neural net where we use filters. So you see these filters over here. We feed these filters into our neural net. That's the main idea. I can go more in depth into the filtering idea if you guys want, but the main usage is for like image recognition, but it's used all over the place. Jesslyn is going to talk real quick about how we used it. But yeah, basically you have this filter that you can slide over your input data, and based on the results of that filter, you perform these neural net operations. So yeah, that's convolutional neural nets. Jesslyn, are you ready to talk? I have this EEG net diagram for you, and we can come back to this after Jesslyn talks, but
yeah, I can talk about it right now.
cool.
All right. So I'm Jesslyn from the machine learning team in this club, and we recently worked on a project where we had to build a machine learning model for the classification of subvocalized signals. So what is that? Like, what is subvocalization? Subvocalization is what occurs when actually, if you like think of a word, there are some minute movements in your muscles that respond to you thinking about that word. And we can use those minute movements to classify like what word you were thinking about and stuff like that. So the goal was to get to create a model for a single participant binary classification that came from an open BCI kit that the hardware team of this club built. And the data team did some pre-processing on it. So we didn't do any pre-processing really, but we got the signals from the hardware team. It was pre-processed by the data team, and then it came to us, right? So, and our model ended up being based on this paper called EEGNet, as you can see, and yeah, so our approach was like this. It wasn't originally, we decided on EEGNet. We actually had two different models going at the same time, but the second model, as we were training, we found out, okay, you know, maybe this one's not as good as EEGNet, so we settled on that. Right, and the model itself works like this. There's some input frequency that you guys can see, right? And then
this is going to be coming from the hardware team and through the data team.
Yeah.
Each of these different channels over here comes from like a different electrode. So we have like 7 or 8 electrodes across a person's jaw, and this is basically just the signal that we read through it and then like cleaned up with the data cleaning techniques.
Yeah. So in the diagram, you guys can imagine that that's data coming to us from the data team, and all of those signals correspond to one word. Right, so it's either like that word, maybe we did a classification of yes and no, so that word could either be those signals could either represent yes or they could represent no, and so that's our input, right? And then we put it through 3 different convolutions. In the diagram, the first one is just called a 2D convolution, which it is a 2D convolution, but I guess to give it a name, it would be a temporal convolution. And what it does is, as you guys can see, it learns frequency filters, right? And so Rohan was talking earlier about Fourier transformations and how we don't really have to do that anymore. And a lot of that is because sometimes with convolution and all this stuff, the filters themselves will learn these frequency filters, and you don't have to do the Fourier transform ahead of time, right? So
yeah, and just some intuition on this thing that they label a kernel over here. This is basically our filter, right? So you can see how it's like longer along the bottom, right? It's like longer width than it is height. That basically just means that when we slide it over our input, we learn these frequency filters, as Jesselyn says, because it's like temporal, right? We're convolving over the x-axis rather than the y-axis, which we'll see over here. So that's why we call it a temporal filter, because it lets us analyze things in the time dimension.
Exactly. And also, I guess just to elaborate on that, so if you have each signal, like 7 signals and, 100 time points, if you imagine it as a 2D graph, your graph might look like 7 by 100 technically, where 7 is the y-axis and 100 is the x-axis. And so even though it is a 2D convolution, our filter is actually like one-dimensional. It's just one by whatever we set the filter size to. So then in the end, like when we cite the filter of the convolution, it filters out each channel at a time instead of like combining channels.
Yeah, also these are like depicted as images, and that might be misleading with this. We're not performing a convolution in the same sense over here where we're handling each of these as pixels. Rather, we're performing these convolutions over the channels themselves. So yeah, like we have these different filters, right? And each of these goes over a single channel. And that's how we learn that. So
yeah, you guys can think of it as like a kind of like a 2-dimensional matrix of just numbers, and the numbers are like the values given to us by the channels. Right?
Yeah.
So that's the first convolution. And the second convolution is a depth-wise convolution, and what that does is it learns the spatial filters that Rohan has been talking about. So like it's also one-dimensional, so it doesn't factor in time at all. And in this case, it learns filters for like the aggregate of all of the channels at this time point to see, okay, like which channel was, the most active or something. And if you map it out, that would correspond to, some part of, because it's like facial / throat muscles, it would correspond to some part, some group of muscles with the most activity on your face or on your throat and stuff like that. And so that's what the second convolution does.
Yeah, and also it can also do some kind of data cleaning in this sense as well, because it might realize, oh, there's this thing that's similar across all the channels. Maybe then I should just throw it out because it looks like some noise that's affecting everything. And it can make some kind of judgments like that. Also notice that there's like multiple of these kernels for every single layer. That just means that we're learning multiple filters, right? Because the more filters we have, the more parameters we have, and the more parameters we have, like the more complex kind of decisions we can make. So that's why we just have multiple kernels for each of these. Yeah.
And so that's the second convolution. And the third convolution is a separable convolution. And it's not really learning any specific filter in this case, but it basically takes what we learned from the first two convolutions, the temporal convolution, depth-wise convolution, and it summarizes those filters, and it kind of combines them into these you can say feature maps, like maps that say like, okay, based on this and this, essentially this is like some sort of conclusion that we could have reached about the first two filters, and it combines them to make these maps. This one's a little bit mind-bending still, even for me, to be honest, but from like the best of my understanding, that's what it does.
Yeah, interesting. Also, just like a quick note about this again, notice how this depth-wise convolution like shortened like this in height, right? Because it basically combined all of these channels into like one flat layer. So that's why we have this output over here like this.
Yeah, maybe I should also mention that that depth-wise convolution is one-dimensional as well. So, well, I think I did mention that. Yeah, and you basically end up with like an output that's one by whatever your first convolution, your temporal convolution, reduced it down to.
Cool.
And then so we put it into the classification, and the classification for our model was fairly simple. We just put it into, we flattened it, right? And then we put it into a linear layer, and from that linear layer, we just took it and we put it into a classification function that's called the sigmoid classification function. And that's because we were dealing with binary classification. So you can kind of imagine it as like the logistic regression, basically, where it pushes each value to one end based on where it is. Yeah.
Yeah, exactly. This can be a neural net. This can be just like a simple function. This can be anything.
Yeah.
But yeah, then we just make that classification. We say, are they thinking a yes or are they thinking a no?
Yeah, and then we output a number like 0 for yes and 1 for no, for example.
Yeah. Cool. Any questions on on this project or how this neural net stuff works. Okay. Cool. So it looks like we have about 15 minutes left. I'll just go over the. Thanks, Jesselyn, by the way. I think that's about it, unless anyone else has questions for her. Okay, cool. So yeah, I think I'll just go over these other neural nets real quick. So there's a ton of different neural net architectures. Convolutional neural nets are a really big one. Another really big one is recurrent neural nets. And then there's also attention-based architectures like the transformer. So a recurrent neural net is basically a when we're dealing with the, so let me give some context. When we're dealing with all of these neural nets, and in our convolutional neural net, you have to have a fixed input size, right? So your input layer over here is going to be three dimensions, regardless of what you do. You can only feed in a 3 vector. You can't, like if you suddenly get a 5 vector for whatever reason, you can't feed it in and assume you're going to get an accurate output. The parameters that you learn over here are only going to work for the dimensionality that you've learned. You can't really change the dimensionality like at any point you want. You'd have to relearn a neural net for that five dimensionality. Similar thing with this convolutional neural net. Your convolution operations are going to have a fixed dimensionality, right? Because we learned these filters, right? This like 24 by 24 by N1 filter. And when we put in like some new kind of some new dimensionality that doesn't fit into that filter, then that's just not going to work. So recurrent neural nets basically aim to fix that problem by allowing you to handle like any dimensionality of input. So you can feed in the recurrent neural net basically feeds into itself. So each time you feed in a new input, it loops back into itself and it takes in another input. So this is what a recurrent neural net actually looks like. If you want to think about it as like a classical neural net, it's like you have the input, then you have like the hidden layers, right? And then you have the output. Whereas if you unfold it, then you get it, then it looks like this, but you shouldn't be confused by this like denotation, like, whoops. This is not the direction of the neural net. The neural net doesn't really feed from left to right. It does in the sense that you're feeding back into yourself, but like the neural net is really like from the bottom to the top, right? You feed in the inputs from the bottom and then you get the output out of the top. So yeah, when you unroll it, you basically it allows you to also see how this is actually going to work in a longer kind of time span. You feed in this first input, right? And then it makes a prediction. You output that. You might use this, you might not. And then it also outputs a value back to itself for the next time step. So then for the next time step, you feed in another input, and then it does the same thing over and over again. So recurrent neural nets are really useful in contexts where you don't know how long your data is, or you're dealing with temporal sequences. So let's say you want to predict like stock prices. RNNs are actually really bad at predicting stock prices, but it's a good example. You can feed in like the value for each day, right? Like the stock price for each day. And then it makes a prediction of what it's going to be the next day. And as you go through this neural net, like as you keep feeding new time steps in, it's going to have more and more context. So it should over time, theoretically, just based on the context, be able to make better predictions for what the next stock price is going to be. It's just like if I can annotate, right? if I give you this dot and I say, okay, this is the stock price on Monday, tell me what it's going to be tomorrow. You really have no context. Whereas if I give you like this graph and I say like, okay, this is the stock price on Monday. What's it going to be tomorrow? You can just generally guess that it's probably going to keep going down. Obviously, that might be wrong. Like, as you see, there's some variance here that might mean, oh, it's going to keep varying and then it'll go up. But the idea is that you have all of this temporal context that the RNN provides that allows you to make better inferences about this. And the thing about the RNN is that you can feed in like as much data as you want beforehand. Like you can feed in like a year of data, you can feed in like 3 days of data, it doesn't really matter. The RNN is designed to handle these kinds of temporal sequences. And it's the same thing for like written text, right? Like RNNs are powerful because like our sentences don't have fixed lengths. You might have one sentence that's like 30 words long and then another one that's only 5 words long. And to handle things like that, that's where RNNs also come in handy. So yeah, is everyone good on RNNs? This again is like a really high level overview. There's a ton of problems with RNNs. They've sort of been abandoned in a standard oops. Oh, I'm still in annotate mode. Sorry. All right. Yeah, RNNs aren't really used that much in NLP anymore, like natural language processing. They're still used in some other like temporal data contexts. But there's still a lot of research into RNNs. They're kind of an elegant way to look at things. I'm currently reading an article about like RNNs learning how to perform stack-based syntactic operations, like how like language is a tree, right? And RNNs are basically able to perform these tree operations by like popping and pushing from a stack that they've found like by basically just looking at the internal weights of an RNN. So that's why recurrent neural nets are kind of cool. But in NLP, at least, they've been replaced by the transformer. I honestly don't think like we have the context here so far on neural nets to really get into understanding what a transformer is. But basically, it uses this kind of attention mechanism to learn where in the data to attend to. So with this RNN, for example, you feed in every single data point, and every single data point is sort of weighted the same, like it gets treated the same as everything else. Whereas with an attention model, you can basically pull out certain pieces of your data and say, this is more important, or these two pieces are related. And that's what a transformer, that's like the basic idea that a transformer is built upon. And if you've heard recently about like GPT-3, like OpenAI's GPT-3, that Elon Musk is like scared about and everything, those are built on transformer-based models. And yeah, transformers currently are most widely used in natural language processing, but they're starting to pick up speed in actually like genomic processing, or what's it called, like bioinformatics, because they can handle these long sequences of data and like construct these huge kind of relationships between different chunks. So yeah, that's what the attention mechanism or transformer is. Yeah, any questions on neural nets so far? I think that's the main stuff over here for deep learning. Yeah, this is like a really interesting area of research. I think like a pretty solid chunk of people who do CS research on campus are working with deep learning. I actually have no idea, but yeah, I'd say a pretty decent amount. Yeah, it's super cool that they can learn pretty complicated kind of information like GPT-3 and stuff. Cool. Okay. All right. Yeah. So we went over this already. Cool. And then just like a quick overview of some libraries and packages that you're going to need if you want to build a project with any of this stuff. For dealing with For like dealing with signal processing for brain-computer interfaces, NeuroPipe is sort of a common one. I believe it is licensed though. EEG Lab and BCI Lab are MATLAB libraries for those. So these two are used more in like a formal lab context, but if you're building a personal project, you're probably going to want to go with OpenBCI or MNE. OpenBCI has a lot of different tools for data processing as well as reading in data from hardware. So this is what we're using for our project, BrainFlow. And then MNE is what our data team is using for all of their data cleaning. It has like inbuilt features for like bandpass, ICA, all kinds of nice things just out of the box. So those are some nice data cleaning libraries for brain-computer interfacing. Then ML libraries, like standard machine learning libraries. Scikit-learn is a really nice one. It has like tons of things out of the box. You can build like a SVM with like 5 lines of code, something like that. NumPy. NumPy is a library for dealing with vectors and tensors. It lets you do like really fast parallelized operations across huge vectors, like lists of numbers that are just like thousands of dimensions. And it lets you do like parallelized dot products and cross products and fancy stuff that you might need. Pandas is for dealing with tabular data, so probably less relevant in a neurotech context. But let's say you have like a table of people with their like ages and like phone numbers and heights and stuff like that. Pandas basically just lets you visualize those and clean and look at that data and do like quick analysis in a nice way. For deep learning, the big 2 packages are PyTorch and TensorFlow. Keras is like a higher level API that lets you write neural nets from like even less code. So like you can write a neural net in like 4 or 5 lines of Keras, whereas with TensorFlow that might be like 15 or 20 lines. PyTorch and TensorFlow are like similar levels of abstraction. Keras is like quite a bit more abstract, but it's still pretty powerful. Everything you can build in Keras, you can build in TensorFlow or PyTorch, but there are things in PyTorch or TensorFlow that you can't build in Keras. Also, Keras has been packaged with TensorFlow since TensorFlow 2. So these are technically, like Keras is technically part of TensorFlow now, but usually when people say TensorFlow, they're referring to TensorFlow proper rather than Keras. There's some technical differences between PyTorch and TensorFlow. We don't have to go into those, but in general, like the current landscape is that PyTorch is used more in research or academia, whereas TensorFlow is used more in production or like in corporate settings. And then Keras is used all over the place. It's more for like quick experimentation with without trying to do too much fancy neural architecture kind of stuff. So yeah, these are some definitely relevant packages. If you do anything in any of these spaces, you're probably going to end up using one of these. Yeah, I think that's about it. So yeah, these are some other, I didn't go too much in depth on like wavelet transform and PCA. So if you're interested on the math on some of these, then totally watch those. But yeah, I think that's about it. This is just like image sources. Cool. Yeah, any questions or anything? I think we're pretty much just perfectly on time right now. Okay. Okay, awesome. I will stop the recording and then this should be uploaded in a few days.